particles. And has subsequently done research in a postdoctoral role at the University of Melbourne in Australia on uranium ore geochemistry. And more recently than that, has worked at University of Strathclyde on nuclear decommissioning. So now Susan has recently joined us here in Leicester in the School of Geography, Geology and the Environment as a lecturer in environmental science. And I'm going to invite Susan to the stage now to present her talk for this evening on metal capture by Tufa. So bear with us while we hand over. And Susan, over to you. I will turn the lights down. Is that low enough? No, not low enough. Let's go to scene 2. There we go. Better? Yes. Right. Thank you, Susan.
Thank you, Tom, for that introduction. I suppose I'll start by say my project on, or my interest in Tufa is really partially a spin-off from a PhD project that never was, and a spin-off from the nuclear decommissioning work that I was involved in at Strathclyde, which essentially was just depositing hydroxyapatite onto cement for capture of radionuclides for nuclear decommissioning of plants. But the Tufa sort of came as a spin-off because of this phenomenon of calcite deposition and capture of metals, or potential of, and so that led me down this track and taking on a PhD student to do some of this work. So what I'm going to talk to you today about is a little bit about the background of natural tufa formation, and then take you to more what the talk is about on anthropogenic tufa and how that captures metals, including some legacy industrial slag and long-term pollution problems, and then some characterization work that I took to the synchrotron here at Harwell in Oxfordshire, and looking at some maps of that, and then rounding up with a short bit on some of what my PhD student Marta at Strathclyde University has been up to on engineering tufa. So those who are not familiar with tufa or travertine, you probably will recognize it now as being a very decorative line product that you might display in your houses. And oh, thank you. Is that better? You can see it now. Yeah. So this product that you might see around your houses and on your kitchen tops as travertine. So this is a limestone deposit, sometimes also known as tufa. Now the difference is tufa is perhaps it's more texturally different to travertine. That is caused by the plants and biota that it covers as it deposits. So this is from mindat.com showing calcite or calcium carbonate encompassing and fossilizing plant and small biota and fauna. And there's an example of a tufa in action that's building up over the top of a waterfall. So it can be what you call a living rock, as opposed to the travertine, which, although has biofilms incorporated into it, operates more in a cave. So there we have our karst system with water percolating through a carbonate type rock and forming stalactites and stalagmites, but more nearer the entrance of the cave, you might get travertine forming. And this, by definition these days, I think is more a hydrothermal process, and CO2 is released following this reaction of bicarbonate and calcium. Tufa, on the other hand, is a similar product, but it's normally operates, so we're looking at this side of the reaction where we have carbon dioxide mixing with calcium-rich groundwater, and this forms a calcium carbonate. So not normally hydrothermal, usually found in rivers or flowing rivers at the surface, quite often as groundwater emerges, which is supersaturated in calcium, but low in carbon dioxide. And as it hits the surface, you get this gaseous exchange where carbon dioxide is incorporated, reacts with the calcium form and forms a carbonate. So it's absorbing CO2. This happens at alkaline or hyper-alkaline pH. So natural tufa is around pH 8, but I'll show you some examples that exceed that. And we get a soft to hard rock going back. Quite often, if it's not with biota, then it can be quite a soft product, but over time that crystallizes to really hard. And part of what my research question would be, how do you get from soft to hard? And this is alive quite often with a biofilm. So my journey took me on search of characterizing and looking for natural tufa. So I found there were 3. I was based in Scotland, in Glasgow, just here. And it took me to a few. So I learnt of 2 up in the Cairngorm, so a very tiny one, St Joseph's Well, and one just down the road, literally at Inchery, which was a much bigger and older one. And probably the most magnificent of one, which I'll show you in a minute, is the one at Burn, and they're all protected. So St Joseph's Well you find it by the side of the road. There's an inscription 1856, and you find a little pipe, and they supply your cup, and you know it's an active tufa because it's forming a little bit on the cup, but just around the corner it's also seeping out of the rock, and here's a mossy bank of tufa. The pH of this one was 7. It had a reasonably high calcium content and high medium content of sulfate, not as high as ones I'm showing, and chloride. So that one was really slow. The Inchery tufa at Cairngorms is really quite ancient, perhaps not as ancient as some of you look at rocks, but in terms of tufa formation, this goes back to 9,700 years before present, up to 6,000 years before present, where this bank here was an active tufa forming. This one is not forming anymore, and I think that's to do with the divergence of the stream. However, we went a bit further upstream, and there's a picture of my poor long-suffering husband collecting water samples for me on field work, but there's some small depositions, and this is an example of some of the more ancient one which might have come home with us. So the pH of this water is 7.9. I suspect that in the autumn flushes where you have a lot of water coming off the peatlands, that the acidic water then washes some of that tufa away, so it never really gets a chance to build up. Calcium is about 60 ppm here, and chlorine about 7.2. The most magnificent of all is by far the Burn at Aberdour in Fife, just north of Edinburgh, and is a cascade type tufa. I suspect, having done a little bit of research in the background, the source of the calcium here is probably gypsum, because we've got quite a high sulfate content and low chlorine and nitrate. This is absolutely covered in mosses and plants, and I think sometimes you can walk past these features and not actually know these are tufa, because it just looks like a bank covered in moss and fern, but actually it's growing and depositioning. There are the presence of, I think I've got that right, stromatolites. So at the bottom, just below the waterfall as it goes into the stream, you've got these pillars of growing calcite and moss coming up, and those are protected. We had to get permission to sample here and promise not to touch those ones. So that's a bit of the background of what I was learning about natural tufa in Scotland, but of course my main objective and interest was to look at anthropogenic tufa and how that might be useful to us in the future. Here is an example of a calcite formation where it's the calcium has leached out of this is a bridge in Mallaig, probably either out of the limestone mortar or the stone, the rock itself, and it's really depositioned at the base of the bridge in quite a sort of interesting formation. So I'm going to take you through how I found these on different types of anthropogenic, perhaps not as beautiful as this, but slag, slag, colliery spoils and paper mills. I'm sorry, I haven't got any pictures of the paper mill, but and how the calcium leaches out of the waste and takes with it the heavy metals. So we identified with my PhD student and our colleagues several occurrences of where anthropogenic tufa had been observed across the central belt of Scotland. Now, the historic bit of the central belt of Scotland is quite deep in coal, steel, slag. There are seams of limestone in patches across, but it's not always that evident. So some of the sources of why this is happening is sometimes a little bit unclear, and it just appears. So we have Airdrie Hill up in the corner, and there's Marta taking a sample. We've got Darnrig, which is colliery. Ravenscraig is a big regeneration site and was one of the biggest coal and steel manufacturing in Europe. And this at Neilston is really quite unusual and quite still a bit of a mystery. So I'll take you. So at Ravenscraig, once they had dismantled, it was a site of the largest steelworks in Western Europe from 1957 to 1992, and that's now all been flattened, and it's one of the largest regeneration brownfield sites of 400 acres. So what they did with all the waste and the slag is they deposited it in this farmer's field at the top here and leveled it all off. So all the rock that you see behind you is not natural at all. This is slag here. And it leaches about where Marta is there, and if you can imagine these photographs joining up, it comes out about here into this lacrustine type environment before it sort of dams up a little bit and then runs down this wetland. And before it gets down to the bottom of the hill, that's gone altogether and crunts up. So Darnrig near Falkirk. So the history of this site's not well documented at all, but the whole area was open cast mining, probably artisan style during the 19th century or possibly earlier. It's been the site of other industry over that time, and this heap is forming from about here where the source is, and it seeps out across this Cowsfield wetland area and all the way down here. The pH from this is about 13 when it comes out of this site, which is super high, and by the time it gets down here, you're looking about pH 7, so it's super gassed out and returning to a much normal pH environment. And this in itself is really quite interesting and one of the advantages. So although it does come out at hyperalkaline, it in a very short space of time has neutralized and normalized, and it's because of this sedimentation and gassing out. Oh, going the wrong way, sorry. So Airdrie Hill is another site that is not well documented, but they're building a housing estate. This is quite new, and they were building it when we were going there. The backfields are the old spoil heaps, and is now going to become, I think, a recreational park. But up the road here was Calderbank, and in the mid to late 19th century, there were 50 collieries locally, ironstone mines, and several furnaces operated by Calderbank Steel and Coal Company. So the site that we were sampling is really quite tiny, although they can all be seen from Google Earth. And it's a little shaft just here, a square sort of drain, if you like, who knows where it comes from. And the pH we measured here was about 11.8 down to 10.6. Neilston, just south of Glasgow, is quite unusual. This is a brown deposit, we think iron rich, and we found that and other metals, including manganese, in there. It's a really, really fast depositioning, and where they've disturbed the site, which has healed up really quickly, or where researchers have gone and chipped away a big chunk, the next time you go, that's almost infilled again. There's also a weird smell of hydrocarbons, so the source is quite unusual or unknown. I had a little bit of dig at the history. I think it might be an opening to a coal mine, as there were some buildings not too far away, but it's got a long, weird history. And it's now the site of a windmill farm. The one I really want to talk to you today, though, is the anthropogenic tufa at Consett on the Howden Burn. This is quite a well-known site, just south of Newcastle, and as a tributary to the River Derwent, is Consett. So Howden Burn goes in there, but the site of the former ironworks here, which operated between 1864 and 1980, as they were operating, they didn't take the slag anywhere. They were just heaping it up by the side, and they just kept pushing it back and back. And over time, this covered up the Howden Burn, and now it's all been tidied up and grassed over. The Howden Burn is still flowing, but it comes just up the top of this through a conduit. And almost as soon as it comes out of the conduit, you get the tufa deposition in here. So the interest in this came, it was a master's student of a colleague of mine, and they had done some work, and they had taken upstream and downstream measurements and upstream and downstream tufa samples of the tufa. And what that came out of that project was that the metals were at quite high concentrations above the tufa, but even in a few meters just below, they'd almost all gone and precipitated out. And as you'll see from the next preceding slides, that's evident in the tufa as well. So I'm sorry, I haven't got the actual details of the water chemistry right here. So we've got in this one, we've got toxic waste, seepage from the slags, dissolving the calcium, mixing with the groundwater. We've got in stream processes of microbes, and then you have metal precipitation, and you get these lamination layers over the season, and they may or may not correspond to the metals, but they certainly are seasonal bands. And as it's doing that, it's taking in carbon dioxide. So I took these samples of the master student Chris's, and we sent them down to the synchrotron, and we did some, it was during COVID, so we did remote access from my office at home, which was fun. And they built the daisy wheel to hold our samples, so there they are. And this is what we got from doing an X-ray map of elements. This one is iron, and the dark bits are where the calcite is, and the iron is showing how it's sort of accumulated around the growths of the calcite. So in more detail with a few more maps, this is a composite picture now showing the calcite, the calcium in grey, and iron in red, but you can see maps of arsenic, calcium, iron, manganese and zinc, and as you can see, they form different patterns. Some of the metals are integral to the calcium, like you can see arsenic shows the same sort of shapes, and then you can see particles in vanadium and zinc showing somewhere between, so you can see some parts of the growths, and there are also some particles there. And iron is just the strongest one, and it was the best map. Looking at the downstream samples, I probably should have pointed out the levels of the heat maps there are quite high numbers. These I've had to turn up the contrast a lot more so you can actually see them, but you have to take my word and read the numbers on the side for me to say that the concentrations were far less than the upstream sample, and the growth not so prominent. With some of the techniques that I use, I can draw lines through the maps and plot up the concentrations of the metals, and I've plotted them on two axes here. So you've got iron, manganese, nickel, lead, titanium, zinc on this axis, and some the elements with lower concentration: arsenic, chromium, copper, sulfur, strontium and vanadium on the lower maps. And if you compare the two side by side, you can see that the concentrations are indeed different as we go from upstream to downstream samples. So we talked about concentrations. Locations we can look about in a little bit more detail. Here's our iron map again, coloured in yellow. But we were able, because it's such a high resolution map, able to extract smaller and smaller, greater and greater detail of these and look at the particles shining there. So this is a composite map showing chromium, lead and iron. And there we see our lead peaks, and this one are zinc and lead here, and the chromium I haven't got a spectrum for, but it was coloured in. So from these maps we can see that it's integral with calcium, like arsenic and vanadium, interstitial for manganese and iron, both with zinc, and the lead, just particles. The lead map, I couldn't really show you because they're just such discrete particles, you wouldn't actually see anything. Some more colours of where I've mixed the elements together just to demonstrate that where those elements are. So the other thing we could do with the analyses was actually look at the form or the type of metals, and we're chasing lead at this point. So we took 3 maps, across this larger map and chased the particles in that. And we can do an X-ray fingerprinting of that and compare that to known materials of lead. So we were chasing lead using this technique called ZANES, which is essentially the X-ray fingerprinting. So just to show you how it works, we've got a lot of different types of lead, from lead oxides, iron and lead, sorbent ferrohydride, acetate, cerussite. So that's the one that is of interest, because that's your lead carbonate and a lead nitrate. And these are the upside down spectra, if you like, showing where the main peak, the inflection point, and the inflection point shows us where the oxidation state is of that metal. So these are our samples. They're a little bit more shaky than our nice known samples. So it's a bit harder to interpret, partly because of the concentration of the particles that we're going through. And if you can just squint your eyes a little bit, and believe me, we have our lead carbonate here and our native lead foil here, and our maps, our spectrum, our fingerprints fall somewhere between cerussite and pure lead. And there's just to show you where we're going. So we can compare spectra from different lead compounds through this linear combination fitting, and we get to lead or cerussite, or a combination of both. So that sort of concluded that work at the diamond synchrotron in Oxford, and this next part of the talk is more on what my student Marta Kalabova did with engineering Tufa in the laboratory. And the way we did this was there was a paper which I should be referencing, sorry, that demonstrated that calcium chloride and ammonia solution, which is stable under normal circumstances, if that's then mixed with 10% carbon dioxide, you can get a precipitation of calcium carbonate, and ammonium chloride is released. So the ammonia here acts as a kind of catalyst and swaps out the chlorine, the chloride for the carbonate partially, and forms carbon dioxide and forms carbonate. So she experimented with lots of different tilts and lots of different media for it to form in. Some of it was cotton wool, clay beads, pure cement, and this one is cement with clay beads embedded in it. And the reason for doing that was to slow down the flow, so it had the solution in our reservoir had time to react with the carbon dioxide, and as it did so, it precipitated this soft calcite material. But what about the metals? So she took that on and mixed the original calcium chloride and ammonium solution with different metals. She tested this in a beaker first, and mixed them with chloride salts of nickel chloride, copper chloride, strontium chloride, and zinc chloride. So the recovery of these were really, really quite high, at 94% zinc, 43 copper, 40% strontium, nickel wasn't so high. So that was in the beaker experiment. But then pushing it down the columns, it changed it a little bit. Zinc still very high, and copper and nickel much better. Strontium not quite so good, and that's the sort of comparison data between the green beaker, the column, and the columns. So in some metals, precipitating it down a column was much more effective than whirring it around the beaker. So in summary, we've got metals incorporated during Tufa formation. We don't know, but it could be sort of colloids or ions. So we've got particles and very small particles, and some are integral with calcite and some are interstitial, so they form around the growths. Both zinc has formed both, and we've got particles of lead, which is probably cerussite or lead and cerussite. So we get this 2-for-1 benefit of metal capture and carbon capture. We find it's feasible within the laboratory. We need to look at perhaps upscaling, because at the moment the concentrations are quite low. What are the effects of the biota and biofilms have on the production of tufa, and whether that makes hard or soft tufa. When it comes to remediating methods, whether we want hard tufa for a permanent capture that you could slice up and perhaps use maybe back into your building decoration, or do we want to keep the soft tufa and use that to recapture the metals and reprocess them? And that comes to the end, and I would like to thank my colleagues at the University of Strathclyde and the University of Glasgow for contributing to these projects. Thank you.
Thank you very much indeed, Susan. Fascinating, so far from my normal research area, of course, but so I learned a great deal there. Now let's leave the full screen so I can see people at home. So please put any questions in the chat if you're watching online, and I'll endeavour to read them out. Can I take any questions from here in the room? I think I have one to start off. I mean, I was just astounded by those sites in Scotland. But are they fenced off? Are they under? Are they being monitored, or are they just little pools of water for people to go splashing around in, unsuspecting on their summer holidays? I don't know. It seems to be quite nasty groundwater bubbling up.
Yeah,
and with unknown sources, quite troubling. how many more sites like that are there, and should we be concerned?
Well, I think there are more to discover. The natural tufa sites are protected, by the way, by Scottish National Heritage, and I had to get permission to go and see those. But the anthropogenic sites mostly found through Google Earth and climbing over fences. I shouldn't admit that publicly. And well, you have the right to roam. So essentially, yes. And one, of course, was behind the housing estate, which was a deep shaft. Although it was very tiny, deep shaft, it could have gone anywhere. The one at Darnrig was in the cow field. Yeah, so they're pretty unknown, I would say. The Neilston one is behind, is now fenced off, and a windmill farm. And so on our last visit, we had to get permission to get onto site. But yes, you could fall down that hole.
Thank you. A question from Mark in the room.
seems going to be equivalent anthropogenic tufa deposits, in the rest of the UK. Would you expect them perhaps to be more prevalent, say, in somewhere like Yorkshire, where you've got that mix of industrial heritage, but also perhaps some carbonate-rich rocks? Has anybody looked to see if they are there or not there?
I think that's yet to be discovered. Certainly you need that mix of slag and calcium in there to form the tufas as it leaches out. So I suspect there are areas around, and I'd be quite keen to go and hunt and look for them and see what else is across the UK.
So if I can ask a question about the projected sort of timescale, if this all goes as you might hope for commercialization, industrial usage, how many years are we from being able to use this for remediation out there in the wild?
I think I'll talk in tasks rather than years. One of the tasks ahead would be to seek out another catalyst, such as sodium hydroxide, perhaps, because ammonium is quite polluting, it causes eutrophication. Seeking out perhaps a sustainable source of calcium chloride, but one of the Solvay process that produces sodium bicarbonate, I think uses calcium chloride as a waste product. And also looking at the biota and increasing the concentrations of the chemicals to have a look. So yeah, there's still a bit of work to do in that space.
Thank you. Right. Well, I can't see any chat questions, or are there? Oh, some hiding. Oh yes. A question from Roy online. So if I read that out for those in the room, have you plans to do similar investigations on lowland tufas, such as in Leicestershire?
I'm exploring my options at the moment. I've got other projects. I've certainly, if there was a willing PhD student, I would be definitely interested in taking it on.
Hint, hint. So yeah. Lots of work to be done for sure. I'm just thinking in this group over the past few years, we've heard about developments in Gowan Jenkins and Dan Smith's research program on deep eutectic solvents, and seeing that go from very, very experimental, hypothetical laboratory experiments to actually a broad array of sort of tests in different circumstances. And I know there are lots of PhD students applying right now to work on those sorts of problems, extracting these rare earth elements, so important for green technologies in novel ways. And so I can imagine, your research sort of snowballing in a similar way. Well, it could do. Yeah. Very exciting to hear about it. Thank you very much indeed. I think we'll. Question from Roger.
Yes, I'm sort of looking at this. If this is a potential carbon capture, you could have. Is it beyond the possibilities of having a major tufa producing unit which carbon captured stuff, stuck it into tufa, and then it just became everybody's work?
Yeah.
Are we talking about an industrialized process that could do that?
Potentially, yes. I don't know how long it takes to go from soft to hard tufa. That's one of the research questions ahead. And I think, as I mentioned, whether your friendly bacterial biofilms are involved in that process, or other processes to make it harder. But yes, I mean, the potential is that you could have lots of pretty patterns with your laminations of metals occurring through that.
I think the soft process, you can sort of stir it to make particular patterns. It's just, it struck me as being sort of slightly bizarre that you could actually have ripples worked out based on a carbon capture process. It's strong. I mean, does it capture large quantities of carbon?
Well, we were using 10% out of the bottles, so potentially, and if what's our atmosphere, 0.3, so potentially, yeah, it's coming down to capturing from atmospheric concentrations of carbon dioxide. I mean, the vision would be to have something that was completely self-sustainable, which wouldn't require much maintenance. So if you just mix the right amount of ingredients together and let it get on with it, as these are happening at Consett, then yeah, I think there could be a potential there to turn it into a material.
Right. Kitchen renovations as a carbon sink for the future. Okay, right, great. Okay. Yeah. Lovely. Right. Well, I think I'll wrap up the meeting now. So it just remains to thank Susan once again for a fascinating talk. Thank you.